Okay, thanks for the kind introduction. It's a great honor for me to be invited to speak at IJTCS. So this is a joint work with my advisor Sanjeev Arora and Yi Zhang. The first introduction. As we all know, convolutional neural networks, also known as CNNs, often perform better than fully connected counterparts, fully connected neural networks, and thus we don't know how good it is. So the question today we want to answer is, can we justify this rigorously by showing a sample complexity separation? Okay, here sample complexity refers to the minimum number of samples that an algorithm to achieve high accuracy with high probability. And the sample complexity separation means to prove an upper bound for sample complexity of CNN and prove a lower bound for sample complexity for SGD on fully connected neural nets on the same task of functions. So the hurdle here is that since ultra-wide fully connected neural networks can always simulate any CNN, it is not clear that how to show SGD plus fully connected nets doesn't learn these CNNs with good generalization. And in this work, we will give a single distribution and a single target function, which can be learned by CNN with constant samples, but stochastic gradient descent on fully connected nets of any depth and any width require at least d-squared samples to learn it. Thus answers the above question. So settings. In this work, we mainly care about binary classification, and domain is always the d-dimensional vector space. We use P to denote the joint distribution on X and Y. And in this talk, this conditional distribution of Y over X is always deterministic, which can be represented by a function H star maps from RD to -1 plus 1. And we use this diamond to denote the composition of this Px, which is the distribution on the input space, is RD, and the H star, which is the conditional distribution of the label over X. And throughout the talk, we will always use this capital P to denote the joint distribution, and this Px for the distribution on the input domain. So also, we'll define learning algorithm. It is a mapping from a sequence of training data to a hypothesis. So A can be random. So to make it more concrete, I will give two examples of an algorithm. The first example is a kernel regression, where this K is a kernel, and here this dagger is pseudo-inverse, and the K xn xn is a empirical kernel n by n matrix on the trained dataset. And also, this is ERM, empirical risk minimization, which is just find the minimizer of among the hypothesis class H, such that the empirical error is minimized. Strictly speaking, ERM-H is not a well-defined algorithm because there could be multiple minimizers. And in this talk, we always consider the worst case performance of all the empirical minimizers in H when we're talking about performance of ERM. So before defining sample complexity, we also need to define the error. So it's very simple. The error of H is just the probability that Hx is not equal to the ground truth Y. And the epsilon delta sample complexity is defined as the smallest number that algorithm A takes to output a hypothesis with at most epsilon error with probability at least 1 minus delta. And we can similarly define the epsilon expected sample complexity. These are our standard notions. And we can also define sample complexity for a family of distributions, which is just taking supremum or max over every over sample complexities for every single distribution. There's a very easy relationship between the n star and n. So therefore, in this talk, we only focused on proof lower bound for this expected sample complexity, which in turn could give a sample complexity for this epsilon delta. So for those who are not familiar with deep learning, I will briefly recap the definition of fully connected neural networks. So fully connected neural networks has bare layers, and this both on W refers to all its parameters. And in each layer, it has a weight matrix and a bias vector. Also, we have this sigma denotes to the coordinate-wise nonlinearity. And in this talk, we are also prove some upper bounds for the sample complexity of the convolutional neural networks. Compared to the FCNets, the CNNs used in this work is very simple. It's just a 2-layer CNN, and it's one-dimensional. Also, it has only one channel, so the convolution kernel is just a k-dimensional vector. And this sigma is a composition of pooling and element-wise nonlinearity. And on top of the pooling, we also have a simple linear classification. Okay, so this CNN is very naive, but the point here is that this naive CNN is enough to prove upper bounds for the hard tasks discussed in this work. So these hard tasks are only hard for fully connected neural networks, but they are very simple even to this naive CNN. So from the expression of this complicated FCNet and this very naive CNN, one can see that it's not possible to separate every learning algorithm on fully connected nets from CNN, as the fully connected nets can just simulate CNN. For example, it can just freeze all the extra parameters and only train those parameters that are shared by CNN. So the question here is really what property of SGD prevents it from finding CNNs among fully connected nets? Okay, so now I will give you some intuition for the answer of the question and also a warm-up example. So the key intuition of this talk is the so-called equivariance, algorithmic equivariance. The definition is here. For learning algorithm A, we call it GX equivariant. Here, GX is some group, and we assume each element of G each element small g belongs to this capital GX. There's a predefined group action which maps the training data set, which maps each element in the training data set to another element in the same space. Okay. So we say an algorithm is GX equivariant if and only if we apply any group action on the entire training data set, and also as well as the test data set, the algorithm A is going to get the same performance. In the case A is random, this requirement becomes these two distributions are equal. Okay, so to give you an example, let's say GX is the permutation group. So a learning algorithm A being permutation equivariant means if you permute the features in your training dataset and test dataset, you're going to get the same test accuracy and the exact correctness for each sample in a test dataset, which sounds very natural and obvious. However, this kind of natural and obvious assumptions or conditions can indeed lead to sample complexity lower bounds. So the main equivariance we will be using in this talk is for SGD on fully connected neural networks is this OD equivariant. Here, OD is referring to the d-dimensional orthogonal group. So this is also known as orthogonal or rotation equivariant. So as in the later of the talk, we will show that algorithmic equivariance constraints can lead to sample complexity lower bounds. However, CNN will not suffer from these lower bounds, which works for free connected neural nets. This is because CNN has convolution and pooling layers, which breaks these equivariance constraints. Okay, so let's see a detailed example. So here we will show that any orthogonal equivariant algorithms, there is a simple problem that CNN can learn with just one sample, but for orthogonal equivariant algorithm, it takes at least omega d samples to learn it. So there are two possible underlying distributions, which is parameterized by this C. C can be either -1 or +1. So the data distribution is independent of C. It's always uniform over its 2D supports. They are E1 to ED and -E1 to -ED. Here, EI is the ith orthonormal basis of the Euclidean space. And the label is just random by 50% probability. Okay, so if we have global average pooling, which means we can first take sum over all the coordinates of xi, then we just need one sample, because in that case, the ratio of the y over the sum of xi can directly tell you what the value of c is. However, if we don't have this global average pooling structure and our algorithm is orthogonal equivariant, which means this constraint set is satisfied, then we claim that no matter what the trained data set is, the function learned by algorithm A on input S must have this form, which is SS x in the product between x and x1 to x and xn. So in other words, the output hypothesis can only use the inner product between the unseen sample and the samples in the trained data set to decide its label. And this is, as you can see, this is a very restricted function class. In detail, it means if there are two different unseen samples, but they have the same inner product against each trained data, then we can imply that the prediction of AS on X must be equal to the prediction of AS on X prime. Okay. And when this n is smaller than d over 2, with at least half probability, this X is going to be new, is not seen in the trained data set. So ASX is equal to this FS000, which means it is a constant or a constant distribution. However, we know in this case, the Y label, the label of the X is still uniformly distributed. So it means the algorithm is going to make at least half error with probability 1/2. Okay, so this finishes the proof of the lower bound. So some related works. This paper by Simon Du, Yining Wang, and Xi Yuzhan et al. Proved that the worst case sample capacity for two-layer CNNs is about the size of its filter, which can be thought as constant, and it's better than the folklore omega d lower bound for linear function class. However, this is indeed not a valid sample complexity separation, as the upper bound and lower bounds are proof for different tasks for different classes of tasks. For example, this lower bound for CNN is, or the upper bound for CNN is proof for a class of CNNs, and the lower bound is for all possible linear functions. So the most related work to this work is probably the paper by Andrew in 2004. He showed that every orthogonal equivariant algorithm requires omega d samples to learn a fixed linear function for all distributions. In other words, if the samples are less than d, then for any orthogonal equivariant algorithm, there will be a distribution such that this algorithm cannot learn this fixed linear function better than like one mass constant accuracy. However, this distribution is the distribution used in the proof of the sample complexity lower bound using DC dimensions, so it can be very unnatural and artificial. So it doesn't imply that a sample complexity separation between fully connected neural nets and the CNN's own image distributions or other natural distributions. So recently, there also have been progress in showing that lower bounds against learning with kernels. So these two papers have both made some progress in lower bounds against kernels. For example, neural tangent kernels, and this one shows some lower bounds for all kernels. Okay, so our contributions. First, we prove that a broad class of gradient-based methods for fully connected neural networks are orthogonal or permutation equivariant. In detail, we identified the sufficient condition for general iterative algorithm to be equivariant, which is very easy to check. And we also proved the sample complexity lower bounds for equivariant algorithms via reduction. So in detail, we show that there is a d square over omega d square over epsilon lower bound for OD equivariance. This is for all distributions and a single quadratic function. And we also show there is a omega d square lower bound for orthogonal equivariance. This lemma is stronger in the sense that this lower bound holds for the single fixed Gaussian distribution and the single fixed quadratic function. So to make it more concrete, to give you some sense that how large this d square could be in practice, I will give you an example. CIFAR10 is one of the most popular image databases in vision tasks in computer vision. It has 50,000 images of size 32 by 32 by 3, where 32 is the height and width, and 3 is the number of channels. Our theorem says that if to learn whether the red channel or the green channel has larger signal strength in the sense of L2 norm, fully connected neural networks needs around 30 to the 4, which is approximately 1 million images if the image distribution is complex enough. For example, it's Gaussian or close to IIT Gaussian. Okay, so this 1 million is very huge. And if you switch to a larger data sets such as ImageNet, and in that case, each image also has more pixels, so these recurrent numbers of images will be even larger. So we also showed the omega d lower bound for permutation equivariant algorithms on single distribution and single function. So in the end, we show that all above problems are indeed very simple problems because they can be learned by this naive two-layer CNN with gradient descent using constant samples. And this completes the separation we want in the beginning of the talk. So in the rest part of the talk, I will first show how to identify algorithmic equivariance. Then I will talk about the lower bounds for equivariant algorithms. So first, this is a notion for general iterative algorithm. The key part of the algorithm is this iterative update rule, which is the current weight and the train data set to produce the next weight. For different iterative update rule and different initialization, this algorithm covers almost every algorithm in deep learning theory, such as SGD with L2 regularization, or you can also have Bechdel. If we allow this iterative rule to use the information of past weight, then it also covers SGD with momentum or Adam or Adagrad. Okay. So among all these iterative algorithms, we are particularly interested in gradient descent for fully connected nets, which is defined here. So we first sample the weights from some initial distribution, and then we do capital T steps of gradient update, and then we output this H, which is the sum of the neural network. So now our goal is to show that gradient descent for fully connected neural networks is orthogonal equivariant, which means our goal is to show this equation. Here, suppose we have two sets of trained data set. The first one is just a normal one, which is xi. The second one is rxi is rotated by this orthogonal matrix R. And we have two sequences of parameters. The first is wt, and the second is w tilde t. W tilde t is trained on this rotated data set. And our goal is to show that at the end of the running, the algorithm will output something like this. If this holds, then we have shown that fully connected neural networks are indeed equivariant. Because if you rotate the dataset, then it's going to give the same prediction. And to prove this goal, we have the following claim, which says that, okay, so first we split the bold font W into two parts. The W1 refers to the weight matrix in the first layer, and W-1 refers to the, all other rest parameters. So we claim that if this condition holds at initialization, then this condition holds for every t. So it's quite obvious that if this claim is true, then this goal is proved. Because if the W tilde 1 and W1 satisfy this condition, it means the output of the first layer will be the same, because this R-1 inverse of R and this Rx is cancelled. So the output of the first layer will be the same. And since the rest of parameters are also the same, it means the output of the neural network will be the same. So we just want to prove this claim by induction. And it turned out to be very simple, just some straightforward calculation. So because of the special rule of this iterative update rule, a special form of this iterative update rule, we only need to show that the gradient also satisfies this condition. That if you switch W1 to W tilde 1, the gradient is multiplied by this inverse of R. So this first line is just very straightforward by chain rule. It is sometimes also known as that so gradient descent is invariant under orthogonal parameterization of the parameters. So for the second equation, it's the same reason as we have just mentioned. This is because W1 tilde by induction hypothesis, W tilde 1 Rxi is equal to W1 Xi. Therefore, the input of the second layer of the neural network is the same. Since the rest of parameters are also the same, they must have the same gradient. And therefore, you use the induction, we have proved our goal. However, this is still a small gap between the goal and the definition of equivariance, of orthogonal equivariance. It is that actually when the trained data sets are rotated by this matrix R, we cannot rotate our matrix, or we cannot rotate our weight matrix W1, W0. This is because the algorithm is always sampled from the same initialization, same distribution. So here we also, for this GD on FC neural networks to be orthogonal equivariant, we also request the initialization of the first layer of the neural network being invariant under orthogonal transformations. In other words, it needs to be symmetric. This is satisfied by Gaussian initialization, IID Gaussian initialization. So the proof is done. And we can extend the idea to the more general case. And we have this theorem, which says that iterative algorithm A is GX equivariant if the following conditions are met. So these conditions looks very messy, and I will just explain them in English. So the first condition says that this function class needs to have enough expressiveness. At least all the functions can be expressed by this parametric model has to be invariant under this group GW. The second condition says that at initialization, this algorithm has to be equivariant, orthogonal equivariant, and this is the induction basis. And the third condition says that the induction can really work. And in practice, and in the case of stochastic gradient descent on free connected neural networks, the third condition is satisfied by chain rule. So 1 and 2 are assumptions, and the third one for the FCNet is usually by chain rule. So here we give more examples of equivariance. So as we can see, from left to right, the level of symmetry increases, and the algorithm is equivariant to a larger and larger matrix group. It's just a diagonal and permutation and orthogonal, and then finally it becomes general linear group. It's a set of all invertible D by D matrices. So as a result, we can prove stronger lower bound from left to right. Okay. And the initialization requirement is that the first layer of the neural network has to be this symmetric or IID or IID Gaussian or zero. This is only for the first layer of this neural network. So we also have some examples for non-iterative algorithms. For example, kernel regression. If kernel is GX equivariant, which means if you apply the group action of G on both X and Y, the kernel value is not changed, then the kernel regression with respect to this K is also GX equivariant. And this has a lot of implications. For example, one of the most interesting cases is the so-called inner product kernel, where the kernel value is the function of the inner product of X and Y. So this includes like linear kernel as well as a polynomial kernel, also the neural tangent kernel. These are all orthogonal equivariant. And as a result, our lower bound can be automatically applied to neural tangent kernel. And another interesting example is the so-called convolutional neural tangent kernel, which is proposed in one of my previous paper with my advisor Sanjeev Arora and Simon Du, Wei Hu, Rosong Wang, and Ruslan Salakudinov. So we should, so this CNTK, it turns out to be translation and flipping equivariant on images, which means that if you just translate the image, or you horizontally or vertically flip the image, the kernel value will not change. And this property turns out to be useful when we want to solve kernel regression with data augmentation. So another example is ERM. If your function class is invariant on this group GX and argument is unique, then ERM is also GX equivariant. So this also allows to prove lower bound for ERM. So now we are entering the last part of the talk. So for lower bounds. I first want to briefly recap some basic notions and some classic upper and lower bounds related to VC dimension. First, this growth function, pi hn, which is defined as the maximum cardinality of these sum patterns, which can be achieved by all the functions in this function class H on all possible choices of x1 to xn, where each of xi belongs to this domain X. And obviously, this pi hn is upper bounded by 2 to the n, and we call the maximum natural number such that pi hn can realize its upper bound, the VC dimension of the function class H. Okay, now this notion is independent of the distribution. It's just a combinatorial definition. And we have the following very famous Shaw-Shadler lemma, which says that if the VC dimension of a function class is bounded, then the growth function groups can be upper bounded by a polynomial whose degree is equal to the VC dimension. And as an application of this South lemma, we have this following classic generalization bound for the function class with finite VC dimension. Here, consistent means a learning algorithm always outputs a hypothesis that achieves zero training error on training data set. So if A is consistent and A's output is always in H, then we have for any distribution Px, the sample complexity is upper bounded by this VC dimension of H over epsilon times log 1 over epsilon. And this upper bound is almost tight up to log 1 over epsilon in the sense that if the number of samples is smaller than this dimension of H over epsilon, then there will exist a distribution P such that the sample complexity of H for this algorithm A on this distribution P will be larger than epsilon delta. Okay, so now we will show how to reduce from standard pack learning to learning with algorithmic equivariance and using this reduction to give lower bounds. We will first need to introduce some more notations. First, we define this composition of Px and G. Here G is a function on, here G is a 1-1 map from X to X, capital X to capital X. And the composition of Px and G is indeed a distribution. And in order to sample from this distribution, one can first sample a random variable from this original Px and then apply the inverse of G on the X. And then we get a sample from this Px, the composition of Px and G. And we can define this similarly for P and G. And one can check that we have this property. So by definition of equivariance, it means that the expected sample complexity of A P epsilon is equal to the expected sample complexity of the composition of P and G and epsilon for any G in this group GX. Consequently, we have the following inequality. This is just taking infimum over this equation for all possible G in this group GX. And this immediately gives us this following lemma, which is the main reduction tool we are going to use. So let A be the set of all algorithms and AGX be the set of all GX equivalent algorithms. We have inequality 4 holds. The proof of this inequality is very simple. We'll just take infimum of equation 3 over two different sets, where this AGX is a subset of all possible algorithms A, so the infimum is larger. And we can also show that the equality is attained when this GX is a compact group. Here, compact means the topology of this group is compact. So it includes the groups such as finite groups and orthogonal groups or special orthogonal groups. So one of the most important implication of compact group is that we can define a higher measure on it, which means it essentially can think it as a uniform distribution on the finite group. And it has this property. And then we construct a new algorithm, A prime, which is defined in this way. We first sample G uniformly from this group GX on this higher measure. And then we apply G on the entire training data set, and we call algorithm A, and we get a hypothesis. And we use this composition of return hypothesis of A and G as our new hypothesis returned by A prime. By the definition of a Howard measure, it's easy to verify that A prime is equivariant because this G is sampled uniformly from this group. So indeed, this is like this G it can hide all the information. If this G is if this group is an orthogonal group, then G is like pick a random rotation. So it's very intuitive that A prime is equal GX equivariant. And the more important thing is that suppose the sample complexity of n star A P composition of GX epsilon is equal to small n. For each G, this A prime can learn with small n samples. So as a result, the sample complexity of A prime over this P cannot be larger than the sample complexity of A over this composition of P and GX. Okay, so one of the particularly interesting special case of this is that PX is invariant under group GX. And in which case means we can take this PX out and rephrase this lemma as in a more elegant way, such that only the function class is augmented. So this is very easy to check. We just plug in P is equal to PX diamond H, and one can immediately get that P circle GX is equal to this. So the take-home message here is that this theorem told us learning under equivariance is as hard as learning an augmented function class by this group GX. And in this setting, and for most of the cases, when GX is compact, this is tight and we don't lose anything. The nice thing about the right-hand side of this equation inequality 5 is that we don't have any algorithmic constraints on A anymore. And so we can use standard pack learning tools, pack learning lower bounds. So here I will show how to use this reduction to show omega d square separation for single function and all distributions. So this construction is very simple, and this is just a quadratic function on the space of R2D. And our theorem says that the sample complexity is at least d squared over epsilon, where there the two-layer CNN architecture can learn it with 1 over epsilon samples. So the gap is d squared. So it turns out we just need to prove the sample complexity lower bound for subclass of this function class achieved by applying GX on this single H star. So recall that GX is all possible orthogonal matrices. Since this ID minus ID is similar to this block matrix U transpose U, this capital H is indeed the subclass of this H star GX, which is defined in this way. And therefore, it suffices to show that the VC dimension of this H is omega d squared. And this is very intuitive, and because the orthogonal group is d times d minus 1 over 2 dimensional manifold, and if we just think about the tangent space at any point, we already get d times d minus 2 over d times d minus 1 over 2 linear space. And so we can prove in this way. We just pick this many samples, which are exactly d times d minus 1 over 2. And we claim that the orthogonal group can shatter these examples. And the proof is just to shatter these examples in the tangent space of the special orthogonal group, which is this small SOD, which is a set of the school symmetric matrices. So when this lambda is sufficiently small, the inner product will have the same sign as this sigma ij. Sigma ij is our desired sum pattern. So for any desired sum pattern, we can always pick sufficiently small lambda and construct U in this way. And the claim is that exponential of U, which belongs to the orthogonal group, can give us this desired sum pattern. Okay. So the upper bound. The upper bound is indeed very trivial. It suffices to construct a CN with constant VC dimension, but still able to express the target quadratic function. So it's just this. It's easy to see that this dimension is at most 4. So remark, the upper bound will still work for two-layer CNs with constantly larger filter size or channels. The point here is just to show that how simple this target is and loss in sample efficiency by ignoring the prior knowledge of the task. That is to learn this with the orthogonal equivariant algorithm. So due to time limit, I guess I will skip the proof for single function and a single distribution. So this is slightly more sophisticated as we are required to, the proof idea is to reduce first is the same reduction. We reduce the sample complexity of equivariant algorithm to the sample complexity of any algorithm with a rich function class. And then we use the classical result from Bendeck and Itai to show that the sample complexity is lower bounded by the log packing number. And we give some detailed, very careful analysis on the geometry of SOD, the spatial orthogonal group, and the proof is done. So, okay, I would like to wrap up my talk. So in this talk, I have shown that I've shown sufficient conditions for iterative algorithm to be equivariant. In detail, there's one particular case that which will be valuable to the community, which is SGD on the neural network with first layer being fully connected and using IID Gaussian. And if this is satisfied, even if the rest of the layers are all convolutional, it doesn't matter. The sample complexity is still going to be d squared, even for single fixed Gaussian and a fixed hypothesis. And you can also use momentum and batch norm and L2 regularization and as much tricks as you want, as long as you can meet the three sufficient conditions. We also show that worst case sample complexity under equivariance constraint is equal to that of the augmented function class. So we show that there is a quadratic function which can be learned by CN with constant samples for any distribution, but learning it on d-dimensional Gaussian distribution requires d-squared samples. Okay, this is the end of my talk. Thank you.
Okay, thanks, Juan, for the nice talk. So let me see if there's any questions from the audience. Oh, by the way, actually, I'm kind of lost in during the talk. How does this group operations work in your proof, showing the gap of the sample complexity? I'm kind of I'm not sure how these group operations will illustrate these kind of things.
Okay, so do you want to go? Do you want me to go back
Yeah, sure. You can talk in a high level sense how these things will make contribute to your theorems.
Yeah, okay, so maybe we'll just go back to the warm-up example. I guess that's the very good illustration. So the warm-up example says that if your algorithm is orthogonal equivariant, then even if you know what this underlying distribution is, like you just don't know the value of C. Even if you know what this PC is, you still cannot get 1/2 error with probability higher than 1/2 if your sample is less than d/2. Okay, so the reason is if you see an unseen sample which is different from every sample in your training data set, then since the algorithm is equivariant, you must make the same prediction for this x as well as this minus x. Okay, because both x and minus x has zero inner product with the samples in your training data set.
Okay.
So they are somehow equivalent from the view of the orthogonal equivariant algorithm. So he's confused by this thing. So he cannot distinguish x and minus x.
Yeah, I see.
Unseen.
Okay. Okay, I did not see any like further questions from the audience. So yeah, and I think it's almost near like lunch times at least in mainland China. So let's thanks Julian again, and thanks for your nice. By the way, there's one more question. So hold on.
Okay.
Like, the question, I'll read this question. Could you please elaborate a bit more applications of proving that some two classes of algorithm to be orthogonal equivalent? So did you get that question?
Okay, I didn't, but I know the question. Okay, the question is, can I elaborate more about the equivariance derivation for the SGD on fully connected neural networks? So, okay, here. So this is indeed proved by induction. So we first want to make sure that at initialization, the algorithm has to be equivariant. And since at initialization, the algorithm hasn't seen the trained data samples, this is indeed a requirement on the initial distribution of the weight, right? Suppose you rotate your weight by some random orthogonal matrix, and this requirement of equivariance, orthogonal equivariance, means the distribution has also to be should be invariant under this orthogonal rotation, because the rotation on the data sample is equivalent to rotation on your weight of the first layer, right? It's just to think about the case of linear classification. Suppose the function is W transpose X. If you rotate X by replace X by Rx, that's equivalent to learning with the same X, but your weight is initialized by R transpose W.
Okay.
Okay.
Okay. So it's almost lunchtime. So let's thank Julian again, and this concludes the IJTCS morning sessions. Thank you,
Okay.
Julian.